How are you all? I hope you all are fine and safe. So today I just came up with another interesting video, and as you can see in front of you guys, uh, there is something written in such a large manner that everyone can just read it. So in this video, what we are going to do is to just prove Euler's formula using some sort of a research paper, that is Vicaria Ghazali. I don't think so I'm pronouncing it correctly, but well, I just got his research paper on a web, and yeah, it's kind of good. I was searching for a better proof for the most famous e to the I x equals cosine x plus I times sine x. So this is what we are going to prove in this video, and I have just checked it out. So he just proved this identity using complex analysis, I think. Yeah, so we are going to use that thing. And yeah, that's not about like the derivative of the cos x plus I sine x and something like that. There is another proof by which like we can just do that proof using derivatives, but I'm not going to tell you that because that is kind of easy. And well, I don't think that if you are finding mathematics easy, then that mathematics is good for you. Should be hard. So there is some information about the researcher, that is Vicaria Ghazali, Mathematics and Statistics Department, School of Computer Science, Bina Nusantara University, Jakarta, like Indonesia. Okay, so let's just get into it. And okay, so here we are going to just begin with introduction. Euler's formula is widely used in solving mathematics or calculus, especially in solving complex numbers. Yeah, that's good. Obviously, it consists of complex unit, that is e to the I theta as cosine of theta plus I sine theta, and where I is just square root of -1, that is a complex unit, right? So yeah, that's correct. Euler's formula is also used in the exact iterative Riemann solver, the approximate Riemann solver of Rho, the Hill Riemann solver. To obtain this model, the author used the derivation from yeah. Okay, so we don't need all these kind of things. We just need to have we just need to get to proof, right? Okay, so the author begins the proof with this thing. I hope you guys are familiar with this, and if you aren't, oh, let me just make you with that. Okay, you know what is E? E is Euler's number, right? Euler's number, but we don't need to know about it deeply. But yeah, why I'm telling you, because there are a lot of representations of E. Like if you look at this formula especially, so well, tell me a value for which tell me a value for which this argument, like I'm talking about this argument, becomes 1, and then we get E. How? So when I is a constant. Well, it's not a constant but is an imaginary unit. So theta is variable. So how can we replace theta so that this argument becomes 1? So well, what I'm talking about is I theta equals 1, then theta is 1 over I, right? So just put theta is 1 over I, just put in the equation and get something. So I times 1 over I equals cosine of 1 over I plus I times sine of 1 over I. And well, if you just look carefully, we're gonna have E on the left hand side. So E comes out to be cosine of 1 over I. How cool is that? And I times sine of 1 over I. More specifically, well guys, I hope you know that 1 over I is just negative 1. No, it's negative, let me just check it out. It's negative I, sorry, not negative 1. So E becomes cosine of negative I plus I times negative I. And again, more precisely, if you say that, well, cosine of negative argument is just cosine it, so E becomes cosine of I. And if there is an argument inside sine which is in form of negative, so this negative comes out of the sine function, so it becomes e to the I times sine of I. So yeah, there is another representation of E that we have derived right before the proof of the Euler's formula. So you can represent E as of this thing, like the trigonometric functions in the argument of I, right? So again, there is another representation of I as let me just erase all the stuffs that I just spread it over here. Yeah, what I'm talking about is E can be represented as limit n tends to infinity of 1 plus 1 over n to the n. Guys, this is very important and you need to remember it. You should remember it, like this is very important. So that's what just written over here. As you can see, limit x tends to infinity of 1 plus 1 over x to the x equals E, right? So that's the author, like the Vicaria, I just forgot his name, Vicaria Ghazali is going to use this thing for his proof, right? Well, let's just get to methods. So what we're going to prove is this beastie object. Okay, let's just get back to mathematics world, results and discussions. Okay, yep. So what we have studied till now is another representation. Well, I'm not going to prove this because but to be honest, I don't know about it. But yeah, if you request me, I will just get a video on the proof of this thing. Okay, well, I have studied this but I'm not sure right now. Well, it's not a big thing. I will just make a new video on it if you want. Okay, so yeah, here the author written, first we find the norm of e to the x plus I times y, right? So the complex complex number in the power of e. So here we have just we have just seen this thing, right? Well, you know what, this argument and this argument are same. What I'm talking about, like, just look, I think this should be written first and then it should be written, but I'm just talking about, well, e to the x is same as limit n tends to infinity of 1 upon x over n to the n. Guys, I'm sorry, but you need to digest it for the sake of like, you just have to digest it. But if you want, I will make sure that I would have a new video on the proof of this thing. Okay, but for now, please just digest it and just continue to prove. So yeah, let's just look. Let put x equals 1. So x equals 1 is just e on the right hand side, and when you just put x equals 1, it becomes 1 over n. So that's the thing. It's not a big thing. Okay, and that's what just written over here, sorted off, right? Okay, well, he just replaced x with z, right? It doesn't mean to anything. Well, z is also a variable, but why did he did that? Because z is some sort of a representation of a complex number, so that's why. But it doesn't mean let x equals a plus ib. We don't mind it, right? Because we are a mathematics student and we know what's a variable and what's a constant. So that's what he did. He just replaced z with the complex numbers x plus iy. Don't get confused, guys. It's just x plus iy, but something misprinting, I think, just happened. So just argument is being replaced by x plus iy, and what he did is just you can just write this as 1 plus x over n plus I y x y over n. So yeah, that's not a big thing. I think the size of the pen is quite big, and I have to just shorten it out. Yeah, that's good. Yeah, okay. So e to the x plus iy is just written like that. This is the real part, and this is, well, it's not the real part of z, because real part of that z was this, but real part is what I'm talking about. Real part of not z but real part, and this is imaginary part. I hope you understood, guys, why I didn't said it is real part of z, because z was only x plus iy. It wasn't a one added left before the x. That's why. Okay, let's just get back to the new page here. Okay, guys, please don't get your mind blown. Just keep your mind relaxed. Okay, well, just for the sake of your knowledge, let x equal, let me just use z, don't mind, a plus ib. So what is the mod of z? That is the absolute value of z, means the, look, what is this, what does this represent? It is a complex plane. Okay. Yeah, yeah, this is what we are talking about, and this is imaginary axis, and this is a real axis. So a plus ib represents, like, just imagine that this is the point where a comma b exist, and b is the imaginary unit, like b lies on here. For your sake of understanding, let b is here and a is here. A is real and b is, well, b is also real, but because of I, it is imaginary part. And if I ask you, just tell me about the imaginary part of z, what would you say? You don't have to say ib. I'm asking you the imaginary part, so I wouldn't come over here. It's just b, and the real part of z is a, right? That's what we're talking about. And when you just ask, let me just make it more clear for you. Yeah, this is what represents. So when you just ask the length of this what do you call cursor, or I don't know what to say, but a bow line. So what do you say? That the length of this I hope you understood, guys. I'm just asking about the length. This is, so this would be the mod of z, that is a squared plus b squared. Because if you have studied, then if let me just make you more clear about it. Let's say that we are having some sort of axis, something like that. Okay, and let's say that this is, so what, this is 0 comma 0, and this is, let's say that x comma y. So the distance between these two coordinates is let's say that it represents d. So d is the square root of x minus 0 whole squared plus y minus 0 whole squared. Well, x minus this 0 and y minus this 0, right? So that becomes just x square plus y squared, and that's what just I have just written over here. So I hope you guys understood it. Okay, so this is the what do you call, the modulus of a complex number. So yeah, that's what the author did here, that the modulus of this thing is just uh, the square root of the imaginary part, that is this imaginary part and the real part. So this is the imaginary part, I hope you remember, and this is the real part. So just and the square root of the square of real part plus the square of imaginary part. And we had n in power as earlier. Let me just fix it. Okay, yeah. So he just solved it out. When you just when you just square it, it's 1 plus x squared over n squared plus 2x over n. And when you just square this, y squared over n squared, and this is just whole to the power 1 by 2 and another n outside the big parenthesis. This is limit, this limit going to infinity. So yeah, that's what just written over here. I hope you understood it. And just take LCM, some sort of LCM, or just take common denominator. So he just took these things inside a parenthesis and one outside it, and this thing is just multiplied with n. So I hope you're clear with that, guys. If you have some sort of doubt, if you have anything, like if you can't understand, you are free to ask me, I'll tell you. Okay, so yeah. Okay, so what he did is e to the this thing. Wait a second, guys, I have to deal with this. How did he did that? X squared plus y squared over n squared, that's good. Limit n tends to infinity. But wait a second. Yeah, guys, I was just searching of like how he just how he just wrote, how he just transformed this thing into this, and I got to have something. Well, guys, if you look closely, then as n tends to infinity, right, that is just helping us out. So yeah, it's a form that we have studied earlier in this video only, that is 1 plus, let's say that it's kn. So one limit n tends to 1 plus kn and whole to the n, and that's a power of 1 over 2 outside this parenthesis. So this becomes just e to the x, like e to the this kn, right? So yeah, that's what the author did. But yeah, he should just mention some sort of steps, because he just jumped off, and I have taken almost 5 minutes to just identify what he did. But yeah, and that's what he did. So there is 1 over 2 on the power as a power on this thing. So when you just take this thing in the power, so 1 by 2, and the n, this n comes out from when you just apply the e to the like this thing. I hope you understood, guys. When you just apply this thing into this, so this, well, yeah, this n appears to be being multiplied with the argument, that is 1 over 2, that was left over in this thing. I hope you guys understood what I want to say. But yeah, that's what I got to know about it. And then if you look closely, let's just move on to further. And when you just multiply this argument in this parenthesis, you're gonna having this only thing, like e to the limit n tends to infinity of 1 over 2 times n being multiplied with 2x over n, it's just x plus x squared plus y squared over its 2 n, right. So yeah, that's what just written over here. And when you just Yeah, when you just look closely, let just put n to infinity in this argument. Okay, so when you just put something divided by infinity, that is 0, right? So yeah, this argument becomes 0 because there was n in the denominator, as we saw. So this becomes 0 and we are left with only x. So yep, so this, like, the modulus of e to the x plus iy becomes just e to the x. And well, if you can just conclude, then you can see that it is not depending, it's not depending on y, right? Yeah. Okay, so for now, as you have saw the argument of e to the x plus iy, so let me just tell you something about what is argument, right? So let me just use this coordinate axis, and let's just use an arrow for our convenience. Let's say that this is what we are looking some sort of. Okay, so we have successfully evaluated what this modulus is, and this is just e to the x, and we are not going to talk about this in this section. Okay, but we are talking about the argument. Argument means the theta, the angle between this coordinate and the x-axis, that is the real axis, right? Keep remember, this is real axis and this is imaginary axis. So I hope you guys have studied about what is argument or what is angle of a line segment. So that is the arc tangent theta, right? And that is, well, let's say that it's x comma y, and x is the real x is the point on real axis and y is the point on imaginary axis. So it's the argument, that is, well, if you if I say more clearly, then this represents argument of, let's say, z. So this is tangent inverse arc tan of the real part of z over the imaginary part of z. So that is what argument of z. And what is that more clearly, this is x over y. So yeah, this is what we are looking for. So yeah, let's well, polar coordinates, this is the polar coordinates, and this is the arc tangent of theta, that is y. No, sorry guys, I did a mistake. That is imaginary over, sorry guys, imaginary, that is, let me just make it slightly clear for you. So yeah, it's imaginary over real. I'm sorry guys, actually it's been a quite year that since I studied this thing. So imaginary of z over real of z. I hope you guys are clear with that, right? Okay, so the theta, it's arc tangent of theta. Well, I'm doing something mistake. Let me just go with this. Let me not teach you by myself, because I'm making some sort of mixed mistakes. So yeah, the tangent of theta is y over x. Then theta is just arc tangent of y over x, and theta is what we are looking for, right? So this is just arc tangent of y over x. Yeah, I'm really sorry guys that I misunderstood. So yeah, here is the representation of theta. Okay, and let's say that just taking power of n both side in this equation. So, well, where this and this, according to De Moivre's theorem, well, I'm not some sort of idea about it, what is De Moivre's theorem, but yeah, let me just try to digest it by myself. This is some sort of equation that De Moivre's theorem says And so okay, so yeah, according to de Moivre's theorem, this equation is valid, and when you just look at what is z to the n is this thing, like what we are talking about, z to the n is cosine to the n theta plus I sine to the n theta. That's correct, but it is correct again because of de Moivre's theorem, that is n times cosine of no, it's not n, but cosine of n theta plus I times sine of n theta, right? So this is the de Moivre's theorem. Well, if you guys want, I would just study about this and I would make a video on it, okay? And I will try to prove this identity. So for the sake of like for now, let's just assume that this is true. So argument of z to the n becomes n times the arctangent of y over x. So far so good. Actually, I haven't studied a lot of things that are being used in this specific video, right? So I'm really sorry for that. And if I would say about me, then I am a 12th standard student from India, guys. So I think that I have I haven't that much knowledge about it, but yeah, I have some sort of knowledge that I can teach you. So that's what really matters. Okay, let's move on further. So e to the x plus I y is just represented, well, yeah, represented like that as we have studied earlier. So as we have seen earlier, right? So just taking argument both sides, so argument of e to the x plus I y becomes limit n tends to infinity of n. Well, n is independent of the argument, so it becomes the arctangent of this thing. And this is, guys, remember that the argument is the arctangent of imaginary over real. So I want you to tell me the well, keep noticing that this is the imaginary part instead of I. This is the imaginary part of this complex number, and this is the real part. So this just goes into denominator, and this will went into numerator, right? So yeah. And in the next step here, the author just dividing and multiplying with n. So I don't know why, but yeah, let's see that. Wait a sec. Yeah, just my mom came here and I have to tell something about her. So yeah, here the author just multiplied and divided with n, and let's see what he did with that. Okay, so when you just look carefully, so when you just multiply this thing, so it becomes n plus n in the numerator, in the denominator, and this becomes, well, this becomes this n and this n cancels out, leaving only y in the numerator. So far so good. So the argument of our complex number becomes limit n tends to infinity of n times the arctangent of this thing over, and then he just multiplied it with this thing and divided with this thing, right? Because I think that there are some properties of limit that says that this thing arc tangent of x over x when limit n tends to infinity is something sort of 1, I think. Let's just check it out. I don't have studied about it. So yeah, because he explained it why limit 10 t tends to infinity. Yeah, so yeah, so finally we got 1, and that's why he just tried to did that. Well, let's see his steps. So arctangent 1 over 1 plus 1. Okay, so yeah, he just I think that what he did, let me just check it out. I think he used by parts. Yep, no, it's he used L'Hopital rule, because there, if you see, if you look closely, there is prime. So yeah, that's what he did, and he got to just get rid of these two things, and this becomes in the denominator, and when he just plug t tends to infinity, this is 0, and 1 over 1 is just 1. So yeah, that's a fantastic job that Vicaria Gazala did in his research paper. So till so far so good. When we are just looking of our case, so then argument of e to the y, that's good, and this is n, well, let me just check it out, n times y, this is n times y, let me just write it clearly, n times y, and in the denominator we had n plus x, that's good. Or this becomes, well, it's also limit n tends to infinity, right? And I think that what he did is again using L'Hopital rule, because in the numerator he is gonna having 1 and in the denominator he is gonna be having x. No, it's 1, because the derivative of x is 0 and the derivative of n is 1, right? So because x is just here, x is a constant, treating as a constant, so he is just having y over 1. He used L'Hopital rule, guys, please be noted, okay? So yeah, the argument of e to the x plus iy, he just successfully calculated as y. And now complex numbers in polar coordinates as z equals r times cosine theta plus I sine theta, where r is the mod z, yeah, and the theta is the argument of z, and we have successfully calculated. Well, tell me guys, what was r, like what was mod z? R, it was e to the x, and what is the argument of z is theta, argument of z is just y. So just plugging these things in our complex equation, and well, he did that, mod of z and cosine of argument of z, then plus I sine of argument of z, that's a good thing. Then, well, keep remember guys, z was e to the x plus y, so e to the x plus y becomes the mod of e to the x plus y, cosine of argument of e to the x plus y, plus I sine argument of e to the x plus y, and we have successfully calculated all these stuffs. Actually Vicaria Gazala calculated. That's really interesting. So what is that? That was this thing, guys, right? E to the x. And what's this? It's this. So yeah, just plugging all the stuffs that we have calculated like he did. So e to the x and cosine of y plus I sine y. So yeah, and then he just broken these two things, and you can see clearly that e to the x and e to the x got cancelled out, and he is successfully having that e to the y equals cosine of y plus I times sine y. And there is a fantastic proof of the Euler's formula. This is really amazing. Well, let's y equals theta, I don't mind. And this is really amazing that he proved it in such a manner that anyone can understand using this thing. That's really amazing. So far so good, guys. Thank you so much for watching this video. Stay tuned for the next video. Have fun with mathematics, because mathematics is something, if you're addicted, you are going to love it, and if you don't, you're gonna hate it. That's what it means. Thank you.